So here I built a module to convert the 3.7 nominal voltage of this 650 battery. 18650 is the form factor of a lithium ion battery. It looks like this. So this is the 7500 milliampere hour, although it's fake. This rating is fake definitely, because the maximum amount of capacity 116,850, sorry, 18650 battery can hold is 3600 milliampere hour. And Samsung also provides this kind of batteries with 3600 milliampere hour, but this kind of company such as, what is the company name here, the company name is Vipa, whatever. Yeah, these are Chinese brands. You can see the Chinese kanjis there, whatever. So these batteries are rated as 7500 milliampere hour, which is completely false claim. Physically and theoretically, it's not possible. The maximum possible is 3600 milliampere hour, whatever. So these are the 18650 batteries, lithium ion cells, and these can supply 3.7 volt nominal voltage. I mean, when it's fully charged, it can supply 4.2 volts, and when it fully discharged, we don't actually fully discharge such batteries, but we say that it's, if it's below 2.7 volts, cut the supply just to save the battery from a deep discharge. So its output range from 2.7 to the 4.2, a single battery, okay, not series, not parallel, a single battery. So yeah, these are the 18650 battery, very famous among hobbyists. So I need a supply to convert that 3.7 nominal voltage into a 5 volt supply for our digital work. For our means, we I am a student of electronics, so in our digital circuit we always need a 5 volt regulated power supply. For that reason, uh, and we don't need very much current, because the ICs has a very high impedance in their input output. That for that reason we can't need very much current, and we can't also take very much output current. I mean, we can't hook up a very heavy load into the output terminal of the ICs. That's a completely different matter. So the main thing is I need a 5 volt supply without much current demand. So for that reason I have used the MT3608 boost converter. This is a MT3608 boost converter which boosts the 3.7 volt. So in this part I have connected the batteries, but our outputs 3.7 volts are connected here, and the outputs are these two black wires are the negative, these two red wires are the positive, and in this output I can get any voltage from the supply to the to around 16 to 20 volts, I guess. But we don't draw that much of a voltage from such modules, because these modules are not that much powerful, and these modules can hardly handle 2 ampere current. Not also 2 ampere, it's around 1.5 ampere. They are saying that the max pulse current is 2 ampere, but continuous current should be around 1.5 or 1.2 amperes. I need high, at max I may need 500 milliampere, but most of the times it's around 200 to 300 milliamperes, so that's not a problem here. So this is the MT3608 boost converter, and this is the everyone's favorite TP4056 lithium ion charging module. So in this module, this IC is the TP4056 IC, which is the main charging and discharging IC here. Sorry, only the charging IC, okay. And in this particular IC there is it's basically dual MOSFET here, and a particular IC somewhere DW10, I guess. If I am saying it correct, then it would be DW10. So this DW10 is the discharge IC, which actually cuts the supply when the battery's voltage falls below the 2.7 volt. So for that reason, this IC 4056 helps the battery to charge, and this IC DW10, this particular IC helps the battery to not to get into the deep discharge mode, because if the battery gets into the deep discharge mode, it might be the it might cause the battery to go dead. I am not sure about it, but we typically avoid deep discharge mode of lithium ion batteries. Deep discharge state, sorry, it's not mode, it's deep discharge state, whatever. So this is the charging module overall. The charging IC is here. The I mean, current limiting factor, or the auto cut feature is in this particular IC DW10, and this is dual MOSFET to limit to actually measure how much current is flowing. There is a very clever circuit using two MOSFET in a single IC. This particular I mean, architecture is very common among different ICs, different modules, because it can easily detect how much current is flowing in the both direction, not only one direction, in the both directions. So this dual MOSFET structure is very common, and I need to study more on this particular topic, because I still don't actually know how this dual MOSFET works and detects the bidirectional current amount, not only unidirectional, it's bidirectional. So whatever, this is the charging module and the cutoff module also, and it actually connects these two terminals are connected into the batteries, and these two are output. So this is the positive and ground of the battery. So this is the positive and the ground of the battery, and this is the positive and ground of the output, and this output got into this ground is directly hooked up into the V in of the module, and the positive supply is connected to a switch. This is a mini rocket switch, single port single throw SPST mini rocket switch, and the output of the switch, I mean the switch, is connected between the V in of the boost converter and the V out of the charging module. So it just connects and disconnects the circuit, and the V and the output terminals of the boost converter, where the 5 volt actually is present, is hooked up to two wires, I mean total four wires, to get this kind of two supply of 5 volt, because our breadboard has two power lines. So for that reason I have built two wires here. So let's attach and measure the out voltages. So we need to look for the positive negative, because if we somehow short these two terminals when the supply is on, the IC will be gone, because there is not any overcurrent or short circuit protection. It's just a bare bone boost converter without any protection. No short circuit protection, no overcurrent protection, no overheating protection, nothing is there. So we have to be very careful when using this IC. So black side is the negative, red side is the positive, so hook up like that, and also for that thing, and this is connected. Let's measure the voltage. First turn on the circuit. The circuit has been turned on. There is the multimeter. This is auto ranging multimeter, so look for the unit also. It might be millivolts, it might be volts. So let's connect. Ground gets connected to the ground terminal, and the positive terminal gets connected to the positive. So as you can see, it's currently at 5.05 volts, and I can definitely tweak that with the provided trim pot. This is a 3296 trim pot built into the module to adjust, I mean there is the knob here, golden color. So we can adjust the output voltage, but as I said, these kind of pots are not to adjust the voltage. It's, I mean, these kind of pots are built to adjust the voltage for a single time. We can't just use it as a analog knob or some kind of a regulator to regulate how much voltage is there, because these are not built like that. These has a very sensitive build inside. Inner build is very sensitive. For that reason we are not able to tweak multiple times, although we can, but it owns up the, I mean it actually damages the internal circuit of the trim pot, whatever. So this is the complete demonstration of such a module, which converts 3.7 nominal voltage of the lithium ion cell, 18650 form factor lithium ion cell, into 5 volt supply for the digital circuit simulation, I mean digital circuit demonstration, with ICs in the 74 series TTL and CMOS also, because 74 HC series is the CMOS series, not the TTL. So it can handle different tasks where the current demand is very minimal, around 1 amps. So this is the complete circuit, and yeah, that's all. So there is basically very simple design: one charging module with overcurrent protection and a voltage auto cut feature, and one boost converter to boost the output of the charging module from 3.7 volts to 5 volts. This is very basic, and this is the main thing. Oh, we have to turn off the multimeter. So this is the actually very complicated design which I built earlier with 2S battery. There is the BMS, there is a boost converter for any voltage higher than the 8.4. Why 8.4? Because boost 2s batteries supply 8.4 voltage and the nominal voltage is 6 point, sorry, 7.4. 7.4 is the nominal voltage. So for any voltage greater than 7.4 I can use the boost converter. Any voltage less than 7.4 I can use two buck converters. I have two buck converters because sometimes I may need 5 volt and 3.3 volt at the same time. And there is also one buck converter which is connected to the BMS power pins to charge the batteries. I will hook up a 12 volt supply here in these two terminals. In these two terminals, 12 volt supply got hooked up into these two terminals, and the output of the this buck converter should be set into 8.4 volts, and that output will feed into the power pins of the BMS, which will charge the battery. This design was very complicated because there was very reverse voltage kick in, and different types of problem with this, because I already burnt one buck converter here, although I changed it. But yeah, this design is not very human. I mean, very good for the circuit, because there should be a Schottky diode, which or MOSFET circuit. Actually, it calls ORing circuit, or ing ORing circuit. So it actually protects any other components from the backfeeding or the what it called, uh, kickback voltage. Any kickback, if any kickback voltage occurs into this the input terminals of this particular buck converter, it may damage this buck or this buck, or in even the this boost converter. So to prevent that, we typically use a ORing circuit consisting either the Schottky diode or the MOSFET. So I did not do that because first of all, I don't have such Schottky diodes with very low voltage, breakdown very low, what it called, VB, uh, knee voltage, very low knee voltage. Or secondly, I don't have MOSFETs, because MOSFETs are expensive. So for that reason I skipped that idea and built a very simple circuit which only give 5 volt supply, and that's all.